Right over here is potential energy. Potential energy, as we all know, is an energy possessed by a body at rest. Once the body is at rest, it possesses what? Potential energy. And this potential energy, we have many types or forms of potential energy, forms in which this potential energy can exist. And number one form of potential energy is gravitational potential energy. Potential energy. This is also its symbol, or its this is just its symbol. You can represent potential energy with this, and it is also a scalar quantity. A scalar quantity measured in joules, also measured in joules. Okay, and the symbol can also be something like EP, E subscript P. Okay, gravitational potential energy is number one form in which potential energy can exist. Number two is elastic potential energy. Potential energy. Number three is chemical potential energy. Number four is our electrical potential energy. Number five, which is magnetic potential energy. So these are forms in which potential energy can exist. Okay, but we are going to take just into perspective these two forms of potential energy. We are going to discuss about just this gravitational and elastic potential energy. So number one, which is gravitational potential energy. Gravitational potential energy. What is gravitational potential energy? This is now the energy. Already we know that potential energy is just the energy possessed by a body at rest. Now gravitational potential energy is the energy possessed by a body at rest due to its what? Height. And once you are talking about gravitational energy, you put due to its height, its position above the Earth's surface or above the ground. Once we are talking about up and down, that is vertical and down, we talk about potential gravitational potential energy. Okay, so when you pick up, let me give some instance. Let's say this is your table. This is our table. This is our table. When we pick up a stone, this is a stone. This is our ground level. This stone possesses zero potential energy. But the moment we pick up this stone from here and put this stone here, this stone now have an attribute of height. There is height now. Once there is height, it possesses potential energy. And the higher the height, the bigger the eyes, or let's say the increase the height, the increase the potential energy. Okay, what is this potential energy that this stone possesses? You know that work is force times distance. When we apply force here and pick up this stone up to here, we are doing some work on this stone, and the work done on that stone is stored in that stone in form of potential energy. When we pick it up, there was no potential energy, but here there is a potential energy, and the work done by picking this stone up to this table is stored in the stone in form of potential energy. And that is the potential energy possessed by that stone. And if this stone eventually falls down, if it falls down from this table, to here, that potential energy that is being stored, that work, when work is done on this stone by bringing it up to this table, and if it falls down, that energy, that potential energy stored in this stone will now be converted into kinetic energy of this stone while falling down. Okay, and the bigger this table, let me say if this table have a longer leg, the bigger the potential energy and the greater the work that you have to do on this stone to take it here, and the greater the potential energy, the increase in our kinetic energy while it starts falling. Okay, this is about gravitational potential energy, and gravitational potential energy possesses the formula that is mg. This is our mass, our acceleration due to gravity, and our height. Okay, this is the mass of the stone. This is the acceleration due to gravity because of height. Once we are dealing with height, we are doing some work against force of gravity. That is this force of gravity. Then finally is our height. Because without height, once there is no height, our potential energy is zero. There is no potential energy, no matter what. So let's quickly go into elastic potential energy. Okay, over here is elastic potential energy. And as we know, elastic potential energy is the energy possessed by a body due towards the deformation of an elastic body. Okay, so if you put a stone in a catapult and we stretch the catapult or the elastic of that catapult, that body, that stone now possesses elastic potential energy. So why do it possess elastic potential energy? Because of what? The deformation or the stretching of that rubber in our catapult. Okay, and once you stretch, or let me say if you're using a bow, once you draw your bow, our arrow now possesses elastic potential energy, and once we release it, that arrow now, that elastic potential energy possessed by our arrow is now transformed into kinetic energy. Okay, so this elastic potential energy, as you all know, is measured in joules, and it is also a scalar quantity. So let's give some illustration about of this. Let's prove our formula using this elastic potential energy. If this is a wall and a spring is being attached to this wall, this is our spring, and this is a load. This is a load. If we stretch this load, let me say in our second diagram is where we stretch that spring. If you check, this spring is being stretched. It is being deformed. Okay, and it goes a distance of x in its deformation. It goes from here to here, which has a distance of x. So if we check this, we know that the force used in stretching this spring is directly proportional to the distance it goes. If we stretch this spring more further, that means we applied more force. Thereby, the force is directly proportional to the distance. If we stretch it small, if we apply little force, it can be here. Okay, so it shows that force is directly proportional to the distance it goes. And this our force, if you remove our sign of proportionality and put our equality sign, it will be equal to, then we put a constant, that is elastic constant, x. Okay, then we put our x. This is the force. Okay, so again, if you now want to get our elastic potential energy, all we need is to integrate this our force. So if we integrate the force, it goes like this, that our force is now equal to the integral of kx, and we are integrating with respect to x, the x, so that here now will be our elastic potential energy. Elastic potential energy, which now will be our elastic potential energy, will now be our k x squared over 2. This thing we did now is integration. If you are finding integration a little difficult, just follow our math section. You will know everything you have to learn about integration. Okay, this is now our elastic potential energy. Let's quickly go over into conservation of energy, the laws of conservation of energy.